Hi, everybody. We're going to do 11.6 now, which is direct products. And it's kind of like in a weird way, it's kind of like the opposite of a subgroup. Meaning you have a group. A subgroup is when you look for groups that are contained within that. A subgroup is when you look for little groups that are contained within a given group. A direct product is when you take a bunch of groups and combine them together to form a giant group, and that's called a direct product. So the direct product, let's look at the definition of it, and we'll see some examples. The direct product. So VI, those are all different individual groups. I'm saying groups. I'm getting ahead of myself. It could be any algebraic system. It doesn't have to be groups. So I kind of got ahead of myself already, but it's still similar to the idea of a subgroup. Anyway, or in reverse. So anyway, all these are all the different operations on all the star I. These are the different operations on the different algebraic systems, and the direct product of these systems with the operations that are defined. These are the elements of V are n tuples. Will form A1, A2, AN, where A1 is part of V1 and A2 is part of V2 and AN is part of VN, all that. And the systems V1, V2, VN, those are called the factors of the giant direct product V. It's interesting how you have the same thing with numbers, where if you have, 12 is equal to 2 times, what's a better example? 30 is equal to 2 times 3 times 5. So 2, 3, and 5 are the factors of 30. So V1, V2, Vn, these are the factors of V. It's kind of interesting. And there are as many operations on V as there are in the factors. And each of the operations is defined component-wise. So if I have A1, A2, AN, and B1, B2, Bn, these are each different elements of V. These are different n tuples. These are 2 different n tuples in V. So if I take A1, A2, AN star B1, B2, Bn, that's going to be A1 star B1, A2 star B2, and so on and so forth. And if I take if I take the A times the B and I diamond it, it's going to be A1 diamond B1, comma, A2 diamond B2, comma, dot, dot, dot. And this is the general definition of a direct product. I hope you're enjoying this so far. I'm going to get my picture at it. Well, I'll leave it over here. How about that? Let's leave it right there. I'm leaving my picture right there, so it's out. No, I'm going to leave it up here, so it's kind of out of the way. All right. Anyway, I just want to refresh the court's memory. A monoid, I don't know if it's monoid or monoid. I didn't really get that right, but it's a set together with a binary operation, and it has the properties that the operation is associative and the operation has an identity. So in a monoid, it's kind of like a group, only it does not have inverses. Now let's just return back to where we were. I'm mentioning that because we're going to see an example of that in just a second. Okay, so back to direct products. Okay, so here we go. Direct product of monoids. So we have so n, the natural numbers, is a monoid because it's associative and has an identity element with addition. So this is really the natural numbers counting 0, which would usually I always learned that was called the whole numbers, but it doesn't matter. It's 0, 1, 2, 3, 4, 5, dot, dot, dot. And then B star is a set of finite strings of zeros and ones with concatenation. Concatenation, as you may recall, is when I just take 2 strings and just join them together into a longer string. And the direct product of n and B star is a monoid. So we're going to illustrate it. And we're going to denote it by a star with this example. So if I have 4, 0, 0, so 4 is a natural number, so number 4, good old plain old number 4. And 0, 0, 1 is the, it's a string of ones and zeros. Then we have, star 3, 1, 1. So 3 again is the plain old number 3. And 1, 1 is a string of two ones. Now, if I join these together, so the first coordinate is going to be 4 plus 3, because I'm doing regular addition of 4 and 3, because we're doing natural numbers with addition. And the next one is going to be 0, 0, 1 plus 1, 1. Now, this plus is really a concatenation, So all it does is that I take the 0, 0, 1, 1, 1. I just take the 0, 0, 1 and then the 1, 1 and stick it all together in one big giant string. And that's my answer. So 4 star, 4 comma 0, 0, 1 star, 3 comma 11 winds up being 7 comma 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1. And 0 comma, now this 0 is the number 0, and this is here is 1, 1, 0, 1, 0. It's just a string of ones and zeros. Star 3 comma 0, 1. So I get 0 plus 3, which is 3, and then I get 1, 1, 0, 1, 0, 0, 1. And 0 gamma star 129 comma 0, 0, 0, 1, 1 is going to be 129 0, 0, 0, 1, 1. And so we're all good. And gamma, as you see, is the identity element of in B, B star, I should say. And 2 comma 0, 1 and 10 comma 8 comma 1, 0. That winds up being 10 comma 0, 1, 1, 0. So that's not a 1, 0. That's the number 10. And 8 comma 1, 0 star 2 comma 0, 1 is 10 star 0, 1, 0, 0, 1. So now, of course, the monoid is not commutative. What is the identity? Well, the identity is just going to be 0 comma gamma. And that's pretty, duh. And that, my friend, is the example of a direct product. So this monstrosity here is a direct product. Alrighty. Okay, now here's a great theorem. The direct product of 2 or more groups is a group. And that is the algebraic properties of a system obtained by taking the direct product of 2 or more groups includes the group axioms, which is, well, that means it's a group. So we're going to present a proof just with 2 groups. And once you see the proof with 2 groups, you could generalize that to more than 2 groups. Just tweak it up a little bit. Anyway, so the direct product of 2 groups is a short way of saying that if G1 and with star 1 operation and G2 with the star 2 operation, if they're groups, then G1 cross G2 with star operation, and because the star it is also going to be a group, where star is the component-wise operation of G1 cross G2. So, and G1 cross G2 is the set of ordered pairs of G1 taken from G1 and G2. So let's look at associativity. So if you have A star parentheses B star C, that's going to be A1 A2 because that's the the set of ordered pairs from G1 and G2. Star B1 B2 star C1 C2. Now I go work inside here, and this star operation gives me B1 star C1 and B2 star C2. These stars are different. The different stars, because this is the star from group 1, that's the star from group 2, may or may not be the same operation. And now that I have this, I star A1 and A2 with this guy here. So it gives me A1 star, this parentheses B1 C1, and A2 star, this parentheses B2 C2. And since these are associative, each individual, this is just all from G1, that's all from G2. And I know that individually they're associative, so I can move the parentheses. Once I move the parentheses, then I can go from this step down to here. See, this is really the key step, right? This right here is really the key step. This is once I've broken into 2 separate two separate groups, that's how I can move the parentheses. I should really say these combined right here, these two, to get from this line to that line, that's really the key of the whole proof. Now the rest of it is just cleaning it back up, just putting it all back together. So this becomes A1, B1, comma, A2, B2, star, C1, C2, which then becomes A1, A2, star, B1, B2, and then star that with C1, C2, which is really just, and that's just another way of saying A star B, star C. So this whole long, messy thing just gave us the associative property. And the associative property, see what it says here, it hinges on the associativity of each factor. And we saw that, and that's what I was pointing out right here in these two lines. Anyways, as far as identity, well, each individual identity is going to be the identities, you know, for this monstrosity. So if you have so I'm going to set E, the identity element, as the ordered pair E1 comma E2, where E1 is the identity for G1 and E2 is the identity for G2. So A star E is A1 A2 star E1 E2, which then becomes A1 star E1 comma A2 star E2, which just becomes A1 A2, which is just my original A. So we see that we do have an identity, and if I do it in the reverse order, it's going to work out the same just as well. And as far as inverses are concerned, again, it's just going to be very similar. It's going to be very similar. That we're going to have that A inverse is just going to be, well, that's the inverse of A1 A2, and that's just going to be A1 inverse comma A2 inverse. But how did they get from here to here? Well, we do that. How do you see that this inverse is equal to that? Well, it's very simple. Let's just multiply them. If A inverse really is A1 inverse, B A2 inverse, let's see what happens when I multiply it by A1, A2. Well, this gives me A1 star A1 inverse and A2 star A2 inverse. But in these worlds, this just becomes A1 star A1 inverse just becomes E1. Don't forget, it's the star one. And A2 star 2 A2 inverse gives me E2, which is the identity element. So we see that this actually worked. Yes, yay, it worked. I'm so happy. I'm so happy as you should be. I'm not actually going to do much with direct products in this course, but I wanted to just show you one nice theorem, Theorem 11.6.8, and again, this is in the same chapter or section, whatever that we've been doing. So if you have if G, which is the ordered pairs of G1, G2, Gn, and then A1, A2, An is a typical element of G. So the identity element of big G is going to be the component with all the individual identity elements. The inverse of a particular element is just going to be the inverse of each coordinate. If I take an element raised to the mth power, that's just raising each, with whatever our operation is. That's just going to be the same as raising each individual component to the mth power. Big G is going to be a billion. A billion means commutative. If and only if each of the individual factors of the G1, G2, Gn are themselves a billion, meaning commutative. And finally, if H1, H2, Hn are subgroups of the corresponding factors, then H1 cross H2 cross Hn is going to be a subgroup of G. That's a really, these are pretty easy to understand and relate to. That's really all I want to do on this. So this is going to be therefore kind of a short video, and we're going to see you next time in the next section. Anyway, everybody, it's been loads of fun and a great thrill, and we'll see you next time. Bye.